Hello everybody, welcome into another lesson. So today we're going to talk about three special types of parallelograms. So in general, in the past couple lessons we've talked about parallelograms where they're quadrilaterals where both pairs of opposite sides are parallel by definition. And then we also talked about with parallelograms how opposite sides are congruent and then opposite angles are congruent and that the diagonals of a parallelogram bisect each other. Well, the following parallelograms I'm about to talk about have all those properties plus additional properties. So for example, everyone's familiar with a rectangle. A rectangle has both pairs of opposite sides parallel to each other. Both pairs of opposite sides are congruent to each other. Therefore, it's already a parallelogram. However, what makes a rectangle special is the fact that it has four right angles. All four angles in it are 90 degrees each. So, definitely opposite angles are congruent. In fact, every angle is congruent to each other in a rectangle. So that's what makes a rectangle special, is the fact that it has four 90-degree angles. And now I have some theorems about some rectangles. It would help if I got an eraser, wouldn't it? There we go. Let's get the eraser. Perfect. So, these are all some short theorems. I have 6 theorems. Don't be overwhelmed by that. We're not going to prove any of them, so no worries there. We're just going to accept them. So, theorem. The first theorem is the diagonals of a rectangle are congruent. Alright, so the theorem states that the diagonals of a rectangle are congruent. So let's draw this rectangle again here with the diagonals. Of course, I have to illustrate that it's a rectangle by putting up the right angle symbols. And why not? Let's name some points, right? A, B, C, D. Alright, so we have rectangle A, B, C, D. Well, if I draw diagonals here, in a rectangle, according to this theorem, we can say that AC, that diagonal, is congruent to BD. So, what does that mean, though? We notice in a parallelogram in general, the diagonals bisect each other. I guess we could call this midpoint of the diagonals E, right? Where in a parallelogram, they would meet at the midpoint of both diagonals, and in a parallelogram in general, they bisect each other, meaning BE would be congruent to DE, so we could definitely mark that. But since they're congruent in a rectangle, that means AE is congruent to CE. That also means that BE would be congruent to CE, and then AE would be congruent to DE. So each of these four parts of the diagonals are congruent to each other. That's what that theorem states about diagonals in a rectangle. So that is a really good thing to know. I got some more theorems about rectangles that I'll illustrate. Alright, rectangle theorems. Actually, I just have one more rectangle theorem. This one is if one angle of a parallelogram is a right angle, then the parallelogram is a rectangle. So this theorem states that if one angle of a parallelogram is a right angle, then the parallelogram is a rectangle. So it's kind of a nice shortcut, so you don't have to sit there and try to determine if all four angles are 90 degrees. So we have here this parallelogram. Well, one angle is a right angle, therefore this would actually be a rectangle. That's what that states. If you can say that even one of them's a right angle, it's a rectangle. Now, there are other quadrilaterals that can have more than one right angle, or a right angle and an obtuse angle in it. But they wouldn't be parallelograms. They would just be quadrilaterals. They'd just be really funky quadrilaterals. But in order for it to be a parallelogram, if one angle has a right angle, then the rest of them would have to also. So that's what this theorem states. That's pretty simple if you ask me. Alright, now I have 3 exercises involving rectangles that we're going to go over what we just learned. We're going to do what we just learned here. So, for the following 3, let's see here. Let me draw a nice rectangle. It'd help if I drew a little bit bigger, wouldn't it? So you could see it. Yeah, let's draw that a little bit bigger. Here we go. We got F, L, A, T. Alright. We got diagonals. This is at point O. Angles 1, 2, 3, and 4. Okay. So it is asserted that quadrilateral FLAT is a rectangle. This is a rectangle. So we're going to do a few exercises here where they give us that the measure of angle 1 equals 18 degrees, right? The measure of angle 1 is 18 degrees. So we need to find the measures of the other angles. Find the measure of angle 2, 3, and 4. This is actually easier than it looks, okay? Let's start with something. We know one's 18 degrees. Well, the diagonals of a parallelogram bisect each other, and the diagonals of a rectangle are congruent. That means that TO would be congruent to AO. FO would be congruent to LO, and then they're all congruent to each other, all 4 pieces. If you look at TOA, that's a triangle, right? So, what does this mean? This means here, if TO is congruent to AO, you have an isosceles triangle, don't you? This is actually going to come in handy, knowing all your triangle theorems. The isosceles triangle theorem states that if two sides of a triangle are congruent, or in an isosceles triangle, that the angles opposite those sides are congruent to each other. So if angle 1 is 18, and this side here is congruent, that means this side is congruent. Angle 2 would also have to be 18 degrees. So based on the isosceles triangle theorem, we know that angle 2 is 18 degrees. Alright, now let's go on to angle 3. Angle 3, however, we know one thing about rectangles. They have 4 right angles, right? So isn't it true that the measure of angle 2 plus the measure of angle 3 would equal 90 to give you the sum of A? So let's illustrate that. So the measure of angle 2 plus the measure of angle 3 would have to equal 90. In other words, they're complementary angles. Well, we know the measure of angle 2 is 18, so we'll put in 18 degrees plus the measure of angle 3. That would equal 90 degrees, which should just then end up giving you that the measure of angle 3 would end up equaling 72 degrees. So we got the measure of angle 3 equals 72 degrees, which just leaves angle 4. Well, let's look at triangle AOL. Hey, AOL, America Online. They're gone now, but little humor. But triangle AOL, we notice again we have an isosceles triangle. And we know about isosceles triangles, the angles opposite those sides are congruent. So that means the side opposite 3 is congruent to the side opposite angle 4. So if 3 is 72, that means 4 is also 72. So the measure of angle 4 would equal 72 degrees. So I thought that was actually very nice that we could apply the isosceles triangle theorem to solve 2 of them, and then just simple complementary angle definition to solve for the measure of angle 3. So that one actually wasn't that bad. Alright, 2 more with rectangles we're going to do. What do we got next? So they give us that FA equals 27, right? FA equals 27. Find LO. Well, this is finding the length of parts of a diagonal. Still not too bad. What do we know about the diagonals of a rectangle? They're congruent to each other, right? If FA is 27, that means LT is also 27. So let's use the fact that LT equals 27. Now, in general, the diagonals of a parallelogram bisect each other, right? And a rectangle is a parallelogram. So what does that mean to find LO? That means LO, if it's bisected, is half the length of LT. So that means LO is equal to half of 27. Which that means LO would then equal 13.5. So LO is 13.5 because that's half of 27. in geometry in general, when you're dealing with geometry, it's good to get either a decimal or a mixed number answer. You generally don't like to leave your results as an improper fraction in geometry. If we were just dealing with strictly algebra, that would be okay. But in geometry, try to either get a mixed number or a decimal answer, preferably a decimal. That's usually your best bet in geometry. But yeah, so we started with the fact that the diagonals were congruent, and then LO is half the length of LT, and then you come up with LO being 13.5. So also not a bad one. And I got one more exercise for rectangles. Then we'll move on to rhombuses. Okay, what do they give us next? So let's see, TO equals 4y plus 7. So this is an algebra one here. FA equals 30. So we have to solve for y. Okay, so what do we know here? TO equals 4y plus 7, right? FA equals 30. Well, let's start with something here. Let's start with something. FA equals 30. That means the other diagonal TL is congruent, right? So TL would also equal 30. Now, the diagonals of a parallelogram and definitely of a rectangle also bisect each other. So if TL equals 30, that means TO is equal to half of TL. So TO equals half of TL. And now TO is given to be 4y plus 7, right? That's equal to half of the value of TL, which would be half of 30. Let me come over here some. So then you still have 4y plus 7 is equal to what's half of 30? That's 15, right? And then this would turn into 4y equals 8, simply giving you that y equals 2. So we found y to be 2. So we started with the fact here, we were given our measurements. If FA is 30, and this is a rectangle, that means TL is also 30. Well, TO is clearly half of TL, so then you just substitute the values in, you come up with the fact that y equals 2. So some of these problems can look intimidating, but when you really understand these theorems, they're really not that bad. Okay, let's talk about a rhombus. Rhombuses you don't hear a whole lot about, yet they're in everyday life. So let me try to draw a nice rhombus here. I can't promise I'll get it perfectly. Okay. So, a rhombus is unique in the fact that it too is a parallelogram, meaning that opposite sides are still parallel to each other by definition. But what makes a rhombus unique is that all four sides are congruent to each other. You have four congruent sides in a rhombus. So it's kind of like a mini parallelogram. You could think of it that way. So yeah, a rhombus is for sure a parallelogram by definition because of the fact that both opposite sides are parallel. That alone's enough to make it a parallelogram. But what makes it special for a rhombus is the fact that all four sides are congruent to each other. So now we're going to have some theorems about rhombuses, and then some exercises about them too. So let's see here. What do we got? Here's a theorem. The diagonals of a rhombus are perpendicular. So this theorem states that the diagonals of a rhombus are perpendicular. So let's illustrate that real quick. Oh, that's definitely turned into a parallelogram, just a general one. I don't quite want to do that. Draw the best rhombus I can. I'll even name this one A, B, C, and D. Let me draw my diagonals here. Okay, so we have here, I better at least label the point where the diagonals intersect. Okay, so by this theorem, then what we have here is that these two diagonals are perpendicular to each other. So what can we say then? We have rhombus ABCD where the diagonals meet at point E. That means that AC is perpendicular to BD. So the diagonals of this rhombus are perpendicular to each other. What else is true about the diagonals of a rhombus? Like a parallelogram, they bisect each other. So AE would be congruent to CE, and then DE would be congruent to BE. So the special thing about a rhombus is that the diagonals are perpendicular, and in general what they have for any parallelogram is that the diagonals still bisect each other. So that still applies too. Alright. And then we're going to talk about another theorem with rhombuses. Let me just fix this here real quick. There is another theorem about rhombuses. No, I don't want to do that. Sometimes I pick up the wrong color. Okay. What is this one? What's the exact wording? Okay. Each diagonal of a rhombus bisects two angles of the rhombus. Okay, so this theorem states that each diagonal of a rhombus bisects two angles of the rhombus. So what does that mean? That means here that you would have angle DAE congruent to angle BAE, right? Because if the angles are bisected, that means each half of the angle is congruent. So angle DAE and BAE are congruent to each other. What else do we know? In general, opposite angles of a parallelogram are congruent, right? And rhombuses are a parallelogram. That means that angle BCE would also be congruent to angle DCE, and as a result, you can then deduce that these four angles here are congruent to these four angles here. And then, if each diagonal bisects two angles of the rhombus, that means angle ABE would be congruent to angle CBE, and then angle ADE would be congruent to angle CDE. And then obviously these four angles would be congruent to each other if they're bisected, right? So that's something unique that rhombuses have that general parallelograms don't, is that the diagonals exactly bisect each angle. And then what else? There was something else about a rhombus, I thought. Oh yeah, this one's easy. This one's real easy. This one's going to be real easy here. So, if two consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. So this one's easy. If two consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. So that's going to make your life a lot easier for proof. So here we have a parallelogram. Well, we have two consecutive sides here that are congruent to each other, right? Meaning one next to the other. In this case, this parallelogram is now a rhombus, simply by the fact that the two consecutive sides are congruent to each other. So that one wasn't so bad. Okay, so now we got three exercises that involve a rhombus. So let me draw this pretty little rhombus here. Let me just label the angles then. So we have angles 1, 2. What other angles do they give us? This is 3 and 4. And then where is angle 5 is down here. Okay. So we have rhombus SLTM. Obviously it's got two diagonals. We have 5 angles. So what is our goal here? We are given that the measure of angle 1 equals 25 degrees, okay? So, in other words, now we're just going to find the other angles. Find the measure of angle 2, measure of angle 3, measure of angle 4, and then the measure of angle 5. Alright, so let's start here. We got the measure of angle 1 is equal to 25 degrees, right? Well, we know one thing, that the diagonals of a rhombus bisect the angles of a rhombus, right? So angle 2 would actually also be 25 degrees, because if angle 1 and 2 are bisected angles of angle S, then that means they're congruent. So the measure of angle 2 is also going to equal 25 degrees. That was a piece of cake, right? Let's actually do angle 5 next. We know also that the diagonals of a rhombus are perpendicular to each other. Angle 5 is right here where the diagonals intersect, so the measure of angle 5 would have to be 90 degrees if the diagonals of a rhombus are perpendicular. Okay, so we found angles 2 and 5, now we just got to solve for 3 and 4. Well, here's something we have to consider. Let's take apart the diagonals for just a minute here, okay? For just a minute. Now, if we don't have the diagonals, we know it's true that the measure of angle 1 plus the measure of angle 2 equals the measure of angle S, right? So that would turn into 25 degrees plus 25 degrees equals the measure of angle S, which then means the measure of angle S equals 50 degrees. Alright, so we found this to be 50 degrees. Well, here's something to keep in mind. Rhombuses are parallelograms, right? Angle L, which is really what 3 and 4 is, it's angle L bisected. It's a same side interior angle to this 50, which would mean that it's supplementary. So angle L is supplementary. So that means what we need to do now is take the measure of angle S plus the measure of angle L. If they're same side interior angles, meaning they're supplementary, set them equal to 180 degrees. Well, we know S is 50, so you'd end up getting the measure of angle L plus 50 degrees equals 180 degrees, which then would simply mean that the measure of angle L, the whole thing, equals 130 degrees. So now we've got the whole L is equal to 130 degrees. This comes back to the theorem about the diagonals of a rhombus bisect the angles of a rhombus, right? So 3 and 4, if you add 3 and 4 together, you get the measure of angle L. Well, for an angle to be bisected, that means it's split into two congruent parts. And by the angle bisector theorem, each part is literally half the whole angle. So we can use the angle bisector theorem to find 3 and 4 right in a row. We know half of 130 is 65. So that means the measure of angle 3 is 65 degrees, and likewise the measure of angle 4 is also 65 degrees. So, starting with these angles, okay, they give us the measure of angle 1's 25 degrees. Well, right away, by the theorem that the diagonals of a rhombus bisect the angles of a rhombus, that means angle 2 is also 25. And then angle 5 is 90 degrees because the diagonals of a rhombus are perpendicular to each other, which means that's a 90-degree angle. And then by knowing that same side interior angles of a rhombus or parallelogram in general are supplementary, and then using the angle bisector theorem, we were able to arrive at measure of angle 3 is 65 and the measure of angle 4 is also 65. So that one also, it looked crazy, but if you're good on your past theorems and the current ones we just learned, then it's really going to go a long way. It's going to help you out tremendously. See, who needs proofs when we're doing these exercises, right? Okay, so what do we have now? We have the measure of angle 1 equals 3x plus 8. The measure of angle 3 equals 7x minus 11. Find x. Alright, so this one's actually not going to be that bad. If we have the measure of angle 1 equal to 3x plus 8, that means it's half of s. That means the measure of angle 2, we can also deduce that the measure of angle 2 is 3x plus 8. So angle 2 is also 3x plus 8, right? And then, if the measure of angle 3 is 7x minus 11, well, so is measure of angle 4. Because in a rhombus, the angles are bisected. So each half of these would be congruent to each other. Now, where am I going with this, you're probably wondering? Well, we know that S and L are same side interior angles, meaning they're supplementary. That's my ultimate goal, is to add them together and get to 180 and then solve for x. But why don't we first break this down into the measure of angle S? We know the measure of angle S is equal to the measure of angle 1 plus the measure of angle 2, right? Which means that it's equal to 2 times 3x plus 8. Because you have two parts that are 3x plus 8, so you just multiply 3x plus 8 by 2, which ultimately means the measure of angle S would equal 6x plus 16. Alright, so we found S. Now let's go for L. The measure of angle L equals the measure of angle 3 plus the measure of angle 4. Which really and truly means it's going to equal 2 times the quantity of 7x minus 11. I could have wrote in 7x minus 11 twice for this, but it would be the same thing as 2 times 7x minus 11. I thought it would just be simpler to distribute. So that means the measure of angle L equals 14x minus 22. Alright, so now we have the measures of angle S and L. If they're same side interior angles, that means they are supplementary. So what that means is that you add them together, you're going to get 180. So the measure of angle S plus the measure of angle L would equal 180. That's the truth. Which simply means now we're going to take 6x plus 16 plus 14x minus 22, set all that equal to 180. So we simplify this, you would end up getting 20x minus 6 equals 180. I'm just making sure I didn't screw up somewhere. Yeah, I didn't. Nope. 16 minus 22 is negative 6. Yeah, all right. 14, that's 20. Okay. So then what you would have last but not least is you would get 20x equals 186, which then we just need to get a decimal. Sometimes you'll have decimal answers, you just will. So let's figure out, as a decimal, what is 186 divided by 20? Come on, calculator. 9.3. So x would end up equaling 9.3. That's what you would get. X is equal to 9.3. So yes, we use the fact that the sums of 1 and 2 is angle S, and the sums of 3 and 4 is angle L. And then the fact that the sum of S and L together is 180, since they're same side interior angles, meaning they're supplementary. So you just add them together and you'll just get 9.3 for your value of X. All right. Wait, why am I erasing that? Okay, so what's the last one on rhombuses? The measure of angle 1 equals 3x plus 1. Boy, they sure love that the measure of angle 3 equals 7x minus 11. They sure want to keep that. Well, this again actually isn't going to be that bad, because all we have now is just like the last exercise. We know that the diagonals of a rhombus bisect each other, right? So that means that the measure of angle 2 would also equal 3x plus 1, and that the measure of angle 4 would also equal 7x minus 11. Alright, well, let's do the same thing. I erased that S completely. I hate when I do that. There's S. Alright. So, angle S, again, the measure of angle S is equal to the measure of angle 1 plus the measure of angle 2, which would have to simply mean that it's equal to 2 times 3x plus 1, which means the measure of angle S equals 6x plus 2. Alright, now the measure of angle L would be equal to the measure of angle 3 plus the measure of angle 4. Which really means it's equal to 2 times 7x minus 11. Which means the measure of angle L equals 14x minus 22. And then we know that S and L are same side interior angles to this rhombus, meaning that they're supplementary. So where we're going from here now is to add those two angles together. Measure of angle S plus the measure of angle L equals 180 degrees. So that means 6x plus 2 plus 14x minus 22 equals 180 degrees, which would break down into 20x minus 20 equals 180 degrees. which would then just give you that 20x equals 200, which means x equals 10. So, much like the last exercise, we start out with the fact that angles 1 and 2 are identical to each other since they're both bisected angles of angle S. And same case with 3 and 4. They're identical because they're both bisected angles of angle L. So we found what angles S and L would truly be. We added them together to come up with 180 because they're same side interior angles, meaning they're supplementary. We ultimately get that x is 10. Alright, I have one more quadrilateral to talk about, or one more parallelogram to talk about. This one's probably the most special of all. I know everyone's familiar with this one. Everyone knows this one. If you guessed a square, you'd be right. That's exactly what it is, a square. So we have a square. Well, a square, much like a rectangle, has 4 right angles. Both pairs of opposite sides are parallel to each other, but all 4 sides are congruent to each other. So, a square by definition is definitely a parallelogram, because both pairs of opposite sides are parallel, but it is also a rectangle in the fact that it has 4 right angles, and it is also a rhombus in the fact that all 4 sides are congruent. So a square is probably the most special parallelogram of all because it is not only a parallelogram, it is a rectangle and it's a rhombus. It's got all 3 in one. That's what a square is. And then remember when we talked about regular polygons, how they have the same number of sides, just for starter. Well, regular polygons, every side's congruent to each other and every interior angle's congruent to each other. So a square is a regular quadrilateral. It's the only regular quadrilateral. I have no real exercises with squares. I think they're pretty self-explanatory. So that's it for squares, but there is a little bit about triangles I have to talk about today. Particularly one theorem about right triangles. And then a few exercises with it. Theorem. Let's see. The midpoint of the hypotenuse of a right triangle is equidistant from the vertices. Alright, so let's draw this right triangle here. Let's draw the fact that this is a right triangle, and we'll call this point D. Okay. So this states here, this theorem states that the midpoint of the hypotenuse of a right triangle is equidistant from the vertices. So what does that mean? Well, D is the midpoint of hypotenuse AC and right triangle ABC, okay? Well, for starters, if D is the midpoint of the hypotenuse, that means BD is the median, right? Because it's a line drawn from a vertex angle to the midpoint of the opposite side. And we know about medians that on the opposite side that it splits into two congruent sides. So AD would be congruent to CD. It's already equidistant from A and C, but this theorem states that it's also equidistant from vertex B. In other words, you would have that AD is congruent to not only CD, it's also congruent to BD. That's what this theorem states. Which also we can apply the fact, if you're looking for angles, that you would end up having two isosceles triangles. So we are going to do a few exercises with the triangles, and then we're done for the day. Alright, what do we got here? Draw a nice big right triangle. GRI. What else do we get from here? Well, first it would probably help if I identified the right angle of this triangle. It's right there. So let's draw this median from the right angle. And at that point, the midpoint is M. Now let me just label the angles. We just have 3 exercises for this, then we're done. So let's see. 1, 2, then this is 3, and this is 4. Okay. So here we have right triangle GRI. M is the midpoint of RI. So the theorem we just discussed was that the midpoint of the hypotenuse of a right triangle is equidistant from the 3 vertices. So we can actually start by filling that out. That means that RM is congruent to IM, which is actually also congruent to GM. So this is going to go a long way here in a second. You're going to see why. It's going to make our life a lot easier. So we got here that the measure of angle 1 equals 32 degrees, right? Now we got to find 2, 3, and 4. Alright, so angle 1 is 32. Well, we have the side opposite angle 1, and then we have the side opposite angle 2, both congruent to each other. That means angle 1 would have to be congruent to angle 2 by the isosceles triangle theorem. So measure of angle 2 equals 32 degrees. So now let's look at something here. Angle G altogether is a right angle, isn't it? That is the right angle of the triangle, which means the measure of angle 2 plus the measure of angle 3 equals 90. They're complementary. So measure of angle 2 plus the measure of angle 3 altogether equals 90 degrees. Which means then you have the measure of angle 3 plus 32 degrees equals 90 degrees. Which then would have to give you that the measure of angle 3 would end up equaling 58 degrees. So we now have that the measure of angle 3 is 58 degrees. Well, let's see, the side opposite angle 3 is also congruent to the side opposite angle 4, which by the isosceles triangle theorem means that angle 3 would be congruent to angle 4. So the measure of angle 4 would then also be 58 degrees. So if you know your isosceles triangle theorem real well and complementary angles, this one was a piece of cake. And 2 more exercises, then we're done for the lesson. All right, what do we got next? Good one. Measure of angle 4 equals 7x minus 3. Measure of angle 3 equals 6 times the quantity of x plus 1. So we got to find x. Well, it still applies in this exercise that angles 3 and 4 would be congruent to each other by the isosceles triangle theorem. So this is actually going to be a piece of cake. All we would have to do is take angles 4 and 3, set them equal to each other. So you'll take 7x minus 3, set that equal to 6 times x plus 1, which then turns into 7x minus 3 equals 6x plus 6, which then means that x equals 9. So x equals 9 due to the isosceles triangle theorem. And I got one more. See how easy that one was? The last one probably won't be quite as easy, but we can rise to the challenge. We got this. All right. This is about the sides this time. So GM equals 2y plus 3. RI equals 12 minus 8y. Find y. Okay, so they give us that GM is equal to 2y plus 3, and then the whole RI, that whole hypotenuse RI, is equal to 12 minus 8y. Well, what do we know here? We know that, again, in a right triangle, the midpoint of the hypotenuse is equidistant from the 3 vertices. So that means that GM is also congruent to RM, which is also congruent to IM. But we have the whole RI. Well, what that would mean is that essentially GM would have to be equal to half of RI, right? Because it's only congruent to each half of the hypotenuse. It's not congruent to the whole hypotenuse. It's just congruent to half the hypotenuse. So really, we get that GM is equal to half of RI. We can start with that. GM equals half of RI, which we plug these in. That means 2y plus 3 equals half of 12 minus 8y. Now we're cooking, because then we have 2y plus 3. Distribute this, you would end up getting that equal to 6 minus 4y. Which would then end up giving you 6y is equal to 3. which then means y is equal to 1/2. Which really we should say is 0.5 because we're dealing with geometry, we should really say 0.5. So let's put this in here. Half of 8 is 4. 12 minus 4 is 8. That'd be 2. That'd be 1 plus 3 is 4. Yep, so these would actually check out. If you put in the 0.5 value for y, you would find that GM is equal to half of RI. So sometimes don't doubt yourself, because you will get decimal answers, and you've done everything right. You will get decimal answers. But that's it for this lesson. Next lesson we are going to talk about trapezoids. So I hope everyone has a great day. Take care.